I'm going to talk about protons, electrons, ions, conductors, insulators, and the law of conservation of charge. If you haven't seen my introductory video on charge and electric forces, you might want to see that first. Okay? Let me now continue. So it turns out that there's a smallest possible amount of positive and negative charge that objects can possess. Remember that amounts of charge are measured in units of coulombs. All right? The smallest amount of positive charge that is possible is denoted by positive 1.6 times 10 to the minus 19 coulombs. The smallest amount of negative charge that is possible is denoted by negative 1.6 times 10 to the minus 19 coulombs. Now let me give you some examples of particles that have the smallest possible amount of positive and negative charges. You might know about particles that make up atoms and molecules. Okay, you may have heard of protons and electrons. All right, protons are positively charged particles that have the smallest amount of positive charge, 1.6 times 10 to the minus 19 coulombs. Electrons, on the other hand, are negatively charged particles that have an amount of charge equal to negative 1.6 times 10 to the minus 19 coulombs. Okay? If you have a hydrogen atom has one proton and one electron. Okay? You add the amount of positive charge to the amount of negative charge, which is a negative number. Those numbers add up to 0. So we say that a hydrogen atom has a net charge or a total amount of charge of 0 coulombs. Okay? And you will see this for atoms that have an equal number of protons and electrons. The total amount of charge is equal to 0. There is no total charge because you have just as much positive charge as negative charge. Okay? Now, on the other hand, if an atom or molecule does not have an equal number of protons and electrons, then it has a net charge. Okay? An atom or molecule that has a net charge is referred to as an ion. Okay? Now, if you take salt that has a net charge of 0 coulombs, okay? If you dissolve it in water, so you create salt water, what happens is the molecules of salt dissolve into atoms. You will have positive ions and you will have negative ions. All right? The net charge of the salt water will be 0, but it'll be filled with positive and negative ions. All right, now let me talk about conductors and insulators. Okay, imagine an object composed of charged pieces, charged components. Okay, they could be ions, they could be electrons, protons, it doesn't matter. Now, some objects hold their charged pieces in fixed positions. They don't let them move around. All right? On the other hand, some objects allow their charged components to move around in response to forces. All right? That's the distinction between conductors and insulators. Conductors allow their charged components to move around. Okay? Insulators do not allow their charged components to move around. See the difference? So, an example of a conductor would be a metal. Okay? Copper. The electrons in copper is a metal, can move around freely. All right? You may have heard of current traveling through wires, such as for a can opener plugged into the wall, or a microwave oven, or a television. Okay? The metal in the wire, the copper most likely, allows electrons to easily flow through the wire. Okay, so metals are examples of conductors. Also, salt water. Remember that in salt water, the molecules of salt dissolve into ions. Okay, those ions can freely move around in the water. Okay, so that's another example of a conductor. And then, what would be an example of an insulator that doesn't allow the charged components to move around? Wood, okay, glass, plastic. Now, I presume that you would not like your loved ones to get zapped by every electrical appliance in your house. So what people do is they don't just have exposed copper wires all over their house. What do you see people do? Don't they wrap the wires in some type of plastic? Okay, so that plastic is an insulator. If you touch the wires, for example, that connect your television to the electrical outlet on your wall, the insulator between your hand and the copper wire won't let you get zapped. It won't let electrons run into your hand, or leave your hand for that matter. Okay, so that's an application of insulators, is to shield humans from conductors with a lot of charge. All right, now let me talk about the law of conservation of charge. Okay, so let me type out the statement of the law so there's no misunderstanding. Law of conservation of charge. The net charge of an isolated system always remains constant. So if you have a system where there is no charge entering or leaving, you cannot change the net charge or the total charge. Okay? Now, you may recall that I talked about mixing neutral salt in water to make ions. Okay, if neutral, that means that you have a net charge of 0, if you didn't know that. Okay, so you have salt with 0 net charge, you have water with 0 net charge, you make salt water, all of a sudden you have all these positive ions and all these negative ions. Does that violate the law of conservation of charge? No, because if you add up the amount of positive charge to the amount of negative charge, remember you'll have numbers with opposite signs, they'll add up to 0. Okay, so you had 0 coulombs before, you still have 0 coulombs after you mix the salt and the water. All right, so you'll always see this happen, that you can't destroy charge, you can't create new charge. This is very similar to the law of conservation of matter, if you're familiar with that. Okay? Now, I'd like you to do some calculations related to what I've been talking about. What if I had a certain number of protons, but I didn't tell you the quantity of protons that I had? Instead, I told you the net charge. Suppose the net charge was positive 1 coulombs. Could you calculate the number of protons? Okay, so remember that the charge of a proton is positive 1.6 times 10 to the minus 19 coulombs. So if you had 1 coulomb, you could calculate the number of protons that corresponds to by finding 1 divided by 1.6 times 10 to the minus 19 coulombs. Okay? And if you did that, you would see that a single coulomb is this many protons. Now, that is a staggeringly large number. And that just goes to show how tiny the smallest possible amount of charge is relative to a single coulomb. All right, now let me have you try a calculation. Suppose that I had a system composed of the following. All right, so I have 1 billion protons and 100 million electrons. Can you tell me what the net charge of that system is? Okay, so pause the video and try to calculate that now if you wish. Okay, so I'll go ahead and calculate it. So the net charge of a billion protons, that's equal to a billion, or 10 to the 9, times the charge of each of the protons. Okay, and now we're going to subtract the negative net charge of the electrons. So that is equal to negative 10 to the 8 times 1.6 times 10 to the minus 19. Okay, another way to say the same thing is to say that we are going to add the negative product. So I could move the negative into the last parenthesis pair there, if you like. Now, calculating what that gives, you will see that the answer is 1.44 times 10 to the minus 10 coulombs. All right?